welcome back to the next segment of catalysis. This is part 3. If you can remember, we have already considered part 1 as well as part 2. In part 1, I told you about what exactly catalysis and the catalyst is all about and the requirement of a good catalyst. In part 2, we discussed about the types of catalysis, within homogeneous as well as heterogeneous, and then we also discussed about the comparison between the two. Now in this particular segment, that is part 3 of catalysis, we will be discussing about the basic steps involved in homogeneous catalysis. The basic steps involved in homogeneous catalysis. So, to begin with now, the very first step, I'll be explaining you step by step so that you understand this absolutely clearly. Again, that is, the first one is called as oxidative addition. Now this is one of the most important steps, my dear friends, as far as the homogeneous catalysis is concerned, and it results in an increase in not only the oxidation state of the metal, but also it results in an increase in the coordination number of the metal which is present in a complex. Now I'll give you a very simple example, and that is, let us consider iron pentacarbonyl, that is FeCO5, and it gives you FeCO4 plus CO. Now it's very evident from this particular reaction that here in this case, in the reactant side, there were 5 coordination number for Fe. Now it has become 4, alright, and plus CO is going to be out, so that means we call this as a dissociation reaction. Okay, we call it as what? A dissociation reaction. Now, FeCO4, I treat this with a molecule of iodine and it results in I2FeCO4. Okay, now if you have a look at this, now what happens is, here the coordination number of Fe was 4, and assuming, okay, I'm using this word, stressing on this word assuming, okay, because there are many other parameters also revolving around that, so I don't want to go into all those pitches. So assuming that CO is neutral, then we say that Fe is 0 valent. Okay, now if you can check it over here, what happens is Fe is along with iodine with a charge of -1 each. So in order to balance our charges, Fe will have a charge of what? +2. So from 0 to +2, so that means it results in an increase in the oxidation state of the metal. Plus the other point is, and that is, here the coordination number of Fe was 4, and now it's 4 and +2, that means it comes out to be what? 6. So coordination number is 6. Alright, so this is as what I was talking about, that the oxidative addition method not only results in an increase in the oxidation state of the metal, but also it results in the increase in the coordination number of the metal in the complex. Now, we talk about the requirements. The oxidative addition method, what exactly it requires. So the requirement is the presence of vacant coordination site. Okay, obviously on the metal. Now what happens is, one of the most primary objective for realizing this particular requirement is that sometimes the dissociation of a particular species may result in a coordinative vacancy. Okay, it may result in what? A coordinative vacancy. Okay, and as a result of which, what happens is, due to that vacancy, that obviously there is a possibility of this requirement being realized, and that is of oxidative addition. Alright, so this was about the first step, and that is called as oxidative addition step. I hope you have understood this. Going to the second step, and that is called as reductive elimination. As the name suggests, it is nothing but, I call this as RE, so I just used the word, it is a reverse of oxidative addition method. Okay, and I give you a very simple example now so that you understand this very well. Let us consider a central metal, that is iridium. Now there are two CO ligands, there are two other ligands, there are two hydrogen as well. So coordination number is equal to 6. Now this loses 2 hydrogen, and as a result of which, what I will be getting is some of this. Okay, so now coordination number is equal to 4. Now the 2 hydrogen is being removed, H plus and H plus is being removed, so which results in the decrease in the charge on iridium. So as I said, it's going to be the reverse of oxidative addition. So the reductive elimination basically results in a decrease in the coordination number as well as a decrease in the oxidation state of the central metal. Okay, now one more thing is, the reductive elimination is related to steric effect. That means, what I want to say is that if the ligand is going to be bulky, if the ligand is what? Bulky, then the reductive elimination takes place more rapidly. Okay, reductive elimination takes place what? More rapidly. So in short, what we need to understand is that greater the charge on the central metal and greater the bulky groups which are being surrounding the central metal, greater is the tendency to undergo reductive elimination. Now generally, the groups which are being eliminated are like this. Okay, that is HH, or sometimes it is RH, or sometimes it is going to be RX. Okay, these are the groups which are being generally, okay, I'm using the word generally, that means the lower molecules are going to be eliminated. Alright, now if I just represent this entire part, now I'm going to combine now both the steps, whatever I have explained. So like if I'm showing, say, n number of ligands being coordinated to the central metal, and then I got another group that is X and Y, it results in ln M, that is the number of ligands attached with M. Now what will happen is there is an attachment of X as well as Y. This is resulting in the increase in the oxidation state of the metal as well as there is an increase in the coordination number of the metal. If suppose n is equal to 1, so here I have got coordination number is only 1, but now it becomes what? 3, right? Now, this is nothing but oxidative addition method, which results in both an increase, okay, in the oxidation state as well as coordination number. But now if I'm going to show a reverse reaction of this, okay, so that means I'm going to get this. So that means this X and the Y bond is going to break down, so that means the coordination number is once again coming back to this, that is 1. That is decreased by 2 units, and there is a decrease in 2 units as far as the oxidation state is also concerned. The coordination number and oxidation state both decreases, and that means this will become a reductive elimination, and that's why I use the word that it is a reverse of oxidative addition technique. You understood this? Going to step number 3, and that is insertion reaction. We have first one is OA, the second one is RE, the third one is insertion. Now what is insertion over here is when a group or a ligand or a simple molecule appears to be inserted in a metal ligand bond, then that particular reaction is called as what? Insertion reaction. Okay, a group or a ligand or a simple molecule which appears to be what? Inserted in a metal ligand bond is called as what? Insertion reaction. Now I'll just explain you how it takes place, and that is, let us consider a manganese complex. Okay, the coordination number is 6. There are 1, 2, 3, 4, 5 CO and 1 methyl group. Okay, so this also can be termed as an organometallic compound. Now, I show an insertion of a carbonyl ligand into this. So, it can be shown in this way. And now, what will happen is, C double bond O, CH3. So you can have a look now. This is the inserted one. Okay, the carbonyl ligand is the inserted one. So what happens is, first of all, the bond between the Mn and the CH3 breaks. And then the carbon of the inserted group forms a bond with both the manganese as well as with CH3. Okay, it's forming a bond with both. And this is called as 1,1 insertion. This is called as what? 1,1 insertion. I give you another example, and that is Mn CO4 and CH3 sulfur dioxide addition. Same way, once again we have carbonyl groups being 4 of them, and now the attachment is like this. So SO2 is being inserted between the manganese and the CH3, and then here you can see this, the molecule which is being attached is inserted as SO2, so the sulfur of that inserted molecule is forming a bond with manganese as well as with CH3. Okay, and this also is an example of what? 1,1 insertion. Right? Now, I give you another example, and that is let us have a look at this particular one. HCOCO4. Now please be very careful that this is cobalt, right? Capital C and small o, and the others are carbonyl. Now I am going to treat this with like this. Carbon atom is 1, this is carbon atom 2. Alright, so this is nothing but difluoroethylene. Now, the insertion is going to take place over here between CO as well as H. Alright, so just have a look at the product, how it is going to be formed. This is carbon atom 2, and this is carbon atom 1. So you can have a look at it. This is a molecule which is going to be inserted between CO and H. So the inserted molecule is forming a bond in such a way that they are being attached to the adjacent atoms of the molecule. Okay, that is, one carbon is getting attached to CO and the other carbon is getting attached to H. Here it wasn't like that. Here in this case, the inserted molecule was forming, the only one atom of that inserted molecule was forming a bond with both of them. See here, sulfur is forming a bond with Mn as well as CH3. Carbon is forming a bond with Mn as well as CH3. But here, in this case, what happens is the carbon, these two carbon are adjacent carbons. So the one carbon is getting attached to CO and the other adjacent carbon is being attached to H. So such type of insertions are called as 1,2 insertion. Okay, what are they called as? 1,2 insertion. So this is what is the difference between 1,1 insertion and the 1,2 insertion. And I'm sure you have understood this very well. Next step, and that is called as migratory insertion reaction. It is migratory insertion reaction, or we can also call it as alkyl migration. Now let us take an example which I considered before during the insertion step, and that is 1,1 insertion. And that is, I have manganese, now this is a complex of manganese. CO is to be inserted in between manganese and CH3. And the product that is going to be formed is going to be this. Okay, between Mn and CH3 the CO is being inserted, right? Such that the inserted molecule, that is the atom of that inserted molecule, that is carbon, is being connected with or linked with manganese as well as with C of CH3. Okay, that's why we call this as 1,1 insertion reaction. The reverse of this is also called as a de-insertion reaction. Okay, now how this reaction actually takes place? It normally looks like that directly a CO is going to be inserted between Mn and CH3 and that's it. But no, it's not like that. C13 NMR C13IR has shown that it's the migration of the methyl group taking place rather than direct insertion of CO. Now how exactly it is? I'll show you. I have Mn Now this is what the reaction is, right? Now this CH3 is now going to get linked with what? Carbon of CO. And as a result of which, what we get is this way, and there is a creation of a vacant site. Okay, there is a creation of a vacant site. Now what will happen is, this CO molecule which is there, that is now going into the vacant site. And as a result of which, what we get is the final product. One, two, three, four, five CO which were already there, and then I show here the inserted CO. Alright, this is the inserted CO, and this is how the takes place the reaction is. Here what happens is, like we show that the CO is being directly inserted between Mn and CH3. No, it's not like that. It's via a migration of methyl group. So here the points which has to be kept in mind is, the first point is no change in the oxidation state of the metal in a complex. Point number 2 is the vacant site has to be generated for the insertion of the new molecule. It can be a ligand or it can be a simple one. And the inserted molecule is going to be cis. Okay, to the Mn C double bond O CH3. You can see, have a look at this. This is MnCO CH3 and this is CO. So both of them are cis to each other. So these are the points which has to be kept in mind for the migratory insertion. Number 1 is, during this entire process there is no change as far as the oxidation state of the metal is concerned. A vacant site has to be created, alright, into which the new group can be inserted. And the new group which is going to be inserted is going to be cis to this particular group. Okay, I mean to the alkyl group which is undergoing migration. Alright, so it should not be trans, it has to be what? Cis. Alright, so these are the points which needs to be taken into consideration when we discuss about the next step, and that is about the migratory insertion, or we call it as alkyl insertion. So far the steps which are being there in front of you is, first one was OA, that is oxidative addition. The second one is reductive elimination. The third one is insertion, and then we talked about that how exactly that insertion is taking place. It's via the migration of the alkyl group. So I hope you have understanding up to this. The next basic step, and that is called as Betahydride elimination. Now basically what is this Betahydride elimination is nothing but that the hydrogen or the proton which is being attached to a beta carbon atom of an alkyl group is basically transferred to the metal of the complex. Okay, this is basically called as a beta-hydride elimination. Now I'll give you a very simple example so that you can understand this entire transfer elimination taking place, and that is have a look at this particular complex, right? Now, if I want to go for this reaction which I was talking about, beta-hydride elimination, the first thing is, this is the alpha carbon which is being directly attached to the metal center, and this is the beta carbon atom, and it contains an H, and therefore it is possible. Okay, that is the first condition. If the beta carbon atom doesn't have an hydrogen atom, finish it off. You cannot go ahead. So this is the very first important condition. Now what happens is this one of the H, okay, gets transferred over here to the RH, thereby resulting in what? Now I'm going to show over here dotted lines, two of them, because this is considered to be an unstable state, alright? Because CH2 double bond CH2, so if you can see this carbon atom, okay, this carbon atom is having 5 bonds, so it's pentavalent. Pentavalent carbon is generally unstable. So I'm going to show this by means of dotted lines. Now this H from here, it has gone to the metal center. Alright, so as a result of which, what exactly happens is the alkyl group which was sigma bonded to the metal center is now being converted into a metal bonded hydride and a corresponding alkene. Okay, because it results in the formation of a double bond. Alright, so this is what happens. Now, as I say, the important conditions which has to be kept in mind, or we say the reaction or this step does not take place if, number one is, if the beta carbon atom of the alkyl group do not have a hydrogen or do not have a proton. Point number two is, if there is no vacant site on the metal, okay, for the hydrogen to be migrated. Okay, there has to be some vacancy over here. Then only the hydrogen from here can go over here. Okay, so if there is no vacant site on the metal for capturing this hydrogen, then of course this reaction doesn't take place. And the third one is, if the beta hydrogen atom cannot approach the metal center, due to some of the other reasons, if it is absolutely impossible for this hydrogen, okay, to leave its position and then get bonded over here to the metal, then also this reaction cannot take place. So these are the basic conditions. Number one is the beta carbon of the alkyl group should have a hydrogen atom. Okay, the second point is the metal center has to have a vacant site so that the migration of H can go into that particular site. And the third one is that due to some of the other reasons, if the beta hydrogen atom cannot approach the metal center, then this reaction doesn't take place. Alright, so this is all about beta hydride elimination, and I'm sure you guys are getting it well.